Alright, this is the review video for Dr. Collini's Chem 2380 Exam 3. So let's take a look at these questions and work through them. So question 1 wants us to identify the correct structure for the following molecule. We can see that it should have a parent chain with 7 carbons in it because we've got hept and one. We know there's going to be a ketone, and that ketone is going to be on carbon 2. So we know that it can't be this one because there's no way to put that on carbon 2. This one's an aldehyde. There's nothing in here that indicates that it's cyclic, so it's not going to be 4. So we know that it's got to be either 1 or 2. And then from there, let's just verify that both of these have 7 carbons. So 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. So it's going to be one of these two. Both of these have the ketone on carbon 2 if they're numbering with the ketone having the lowest number. But molecule 1 has the methyl groups on carbon 3 and molecule 2 has the methyl groups on carbon 5. So because we needed it to be 5,5-dimethyl, the correct answer is going to be B. Okay, moving on to question 2. Question 2 asks us to identify the major steps involved in an electrophilic aromatic substitution reaction. So we know that generally that's going to, an EAS reaction is going to start with a benzene ring. It's going to add an electrophile. There's going to be an intermediate where you've added the electrophile but there's still a positive charge. And then the ring gets deprotonated to reform the aromaticity. So this is the general steps that we're going to take, but we know that benzene is incredibly stable due to its aromaticity. So before it's able to react with the electrophile, we need to do something to make the electrophile electrophilic. So it's not going to react with some of our normal substituents that we've seen with double bonds before. So step 1 is always going to be formation of the electrophile, which when I'm looking at these multiple choice answers, the only one that accounts for that is option D. So it looks like D is going to be our correct answer because it starts with formation of an electrophile, and then that electrophile reacts with the benzene to make the arenium ion, which is this product, and then we deprotonate to restore aromaticity, which is this product. So it looks like D is going to be our correct answer, but let's just quickly go through the other options. So B and C both start with a deprotonation of the ring. A deprotonation of the ring, which if we were to do that, it would end up looking something like this, but without that substituent. But we'd have the ring with a positive charge, which is going to be less nucleophilic than what we started with, which was a ring without a positive charge. So we know that deprotonation can't be the first step because we want to keep the ring nucleophilic. And then option A is basically the same as option D, but just without that formation of the electrophile, which we know is necessary for this reaction to take place. So A also is not the correct answer. So that leaves us with D being correct. So question 3 says, which of the following compounds would be most reactive toward electrophilic substitution? So let's try to identify which of these are activating and deactivating groups. So option 1 is oxygen. We know that oxygen has 2 lone pairs, and these lone pairs are capable of resonating into the ring. Those are going to add electron density to the ring, which means that these are activating. So I'm going to put a little A here for activating. The methyl group is weakly activating because it doesn't resonate into the ring, but it does have a little bit of electron density that it's willing to donate. So this is also weakly activating. Bromine is electronegative, so it's going to inductively pull electron density away, but it is capable of resonating electron density in because it does have all of these lone pairs. So it is weakly deactivating because halogens are the one exception where the inductive effect is stronger than the resonating effect. So this is weakly deactivating. Number 4, CHO, that's an aldehyde. So if we wanted to redraw it, we could like this. So this one is not capable of resonating into the ring, but it instead resonates its electron density out of the ring because it can put the electrons in that double bond can resonate up onto the oxygen, creating a positive charge here, which can then be filled using one of the double bonds inside the ring. It can flip up here, put a positive charge here, and a double bond here. So this is going to pull electron density out of the ring. So this is going to be deactivating. And a nitro group does the same thing. It, both through induction and resonance, is going to pull electron density out of the ring. So that is also deactivating. So of all of these options, the most reactive is going to be the one that is most activating, which is number 1, the phenol. So A is the correct answer. Question 4, what is the predicted product of the reaction shown? So we've got 1-hexanol reacting with PCC in the presence of dichloromethane, which is CH2Cl2. So 1-hexanol with PCC, that is, let's draw that out in bond line structure. So that's going to look like this. So we've got 1, 2, 3, 4, 5, 6 carbons with an alcohol on position 1. So this is a primary alcohol reacting with PCC, which should create an aldehyde. So 1, 2, 3, 4, 5, 6 carbons. And then an aldehyde where the alcohol used to be. So we oxidized an alcohol into an aldehyde. The only option in our multiple choice for an aldehyde is option A, which is hexanal. So we know it's an aldehyde. Option A is the only multiple choice option with an aldehyde because B, hexanoic acid, is a carboxylic acid. C, hexanone, is a ketone. D, 2-chlorohexane, that's not the reaction that took place. And E, 1-hexanol, we know that the reaction happened, so it's not E. So A is the correct answer. Question 5, compound A on ozonolysis yields 2 products shown. What is the structure of compound A? So we know that ozonolysis is going to break a double bond and add oxygen on both sides. So we could almost just imagine taking this and putting it like basically right on top of the basically lining up the double bonds and then eliminating the oxygen. So that's what our structure is going to look like. Just instead of having the double bond to the oxygen, it's just going to be one double bond to both products. So let's draw that. So compound A is going to be a benzene ring with a double bond with this ketone, but instead of having the oxygen up here, we're just going to add that structure. So hydrogen on this side, ethyl group on this side, and then don't forget to draw in your double bonds for the benzene ring. So if we started with this structure, added O3-DMS, the double bond would break right down the middle and we would get these 2 products. So now let's figure out which of these options looks like compound A, and it looks like I is going to be the correct answer. So we can see that we've got all 4 of them have the benzene ring, but this one is the only one that has the methyl group on the same side as the benzene, and then the ethyl and hydrogen on the other side. So I corresponds with A, so A is going to be the correct answer for question 5. Question 6, what is the predicted product of the reaction shown? Oh no, the reaction is not shown. Let's go find that. Right. I don't know what happened to that question, but I've copied it back in. So what is the predicted product of the reaction shown? So we've got an aldehyde with an alcohol on its end reacting with H2SO4. And it looks like we're going to form a ring. It's just a matter of how this ring is going to form. So let's think about what is the most nucleophilic and what is the most electrophilic position on this molecule, because we know that it's going to be some sort of intramolecular reaction based on all of our possible products. So the most electrophilic position is likely going to be this alpha carbon here. And we know that because this double bond is capable of resonating up onto the oxygen, and when it does that, we are left with a single bond between the carbon and oxygen, 3 lone pairs up here, so there's a negative charge on the oxygen and a positive charge on the carbon. So this resonance structure with the partial positive on the carbon is the most electrophilic position on this molecule. And then the most nucleophilic is going to be the alcohol, since the alcohol has 2 lone pairs, the thing that's capable of reacting, because all of these carbon hydrogens in the middle aren't going to do any reacting. So if the alcohol attacks, it's going to form a bond at the alpha carbon, which is the most electrophilic position. And when we do this, we're going to form a ring structure. So if I were to number this ring, I'm going to say that the alpha carbon is position 1. So we've got 1, 2, 3, 4, 5. And then the oxygen is position 6 of the ring. So that structure is going to look like this. Okay, so if this is position 1, 2, 3, 4, 5, and 6, we know that there's going to be this oxygen coming off of carbon 1. So let's draw that in. And we know that this oxygen still has a hydrogen attached. So let's draw that in as well. Okay, so that's what the structure looks like after the oxygen attacks. If we put our formal charges in, we know that this oxygen has 3 lone pairs because it had 3 lone pairs to begin with. So it's still going to have a negative formal charge. And then our other oxygen has 1 lone pair and 3 bonds, so it's going to have a formal charge of +1. So to balance these charges, we're going to need to deprotonate the oxygen on position 6, and we're going to protonate the oxygen that's connected to the carbon at position 1. And we can just show this as another intramolecular interaction. So I'll just show this oxygen grabs that hydrogen, and then we are left with our final product looking like this. Which looks to me like answer choice 1. This is the only one that has a 6-membered ring with the oxygen and the OH group on neighboring positions. This is a 5-carbon ring. This is a 5-membered ring, sorry. This is a 6-membered ring, but it doesn't have the oxygen. This is 6-membered, but it doesn't have the OH group substituent, and this is a 5-membered ring. So option A is the correct answer. Question 7. Which of the following statements is consistent with the mechanism for an acid-catalyzed addition of an alcohol to an aldehyde or ketone? So we're trying to go from something that looks like this to something that looks like this, where that R group can be an H or an alkyl substituent. So how do we get from a ketone to the acetal? If it's acid-catalyzed, we're likely going to need to start with a protonation step. So let's show that. So if we start with a ketone and we add acid, one of these lone pairs can come in and grab that acid and protonate, forming the ketonium ion. From here, there's a resonance structure where the double bond can resonate upward. So we'll have a single bond to the oxygen, a positive charge on the carbonyl carbon. This is in resonance, so we're going to add resonance brackets. And then, now that we've got that carbocation, we can have a nucleophilic attack, and we can have a weak nucleophile because we've made the electrophile sufficiently electrophilic with that carbocation. So I'm just going to use water as my nucleophile. Water has these two lone pairs. Those are capable of attacking right here where that carbocation is. And when it does that, we end up with a product that looks like this. Oh, I forgot to show. Oh, never mind. So we end up with a product that looks like this. And then we can have one more base workup step to deprotonate the OH2 group. So I'm going to just show a base. It's likely just another water or something in solution that's able to use its electrons to deprotonate, forming our final product, which is the acetal. So let's put those steps into words. So the first step was a protonation. So that looks like A and D are the only ones that start with a protonation. Step 2 is a nucleophilic attack, which looks like option A is likely, oops. It's looking like option A is going to be our correct answer. Option B says a nucleophilic attack with a protonation. That's not what we would do for acid catalyzed. C is nucleophilic attack. You do need a workup, or you don't need a workup, so not C, and then not D. So A is the only answer that matches what we have shown here. Question 8, which reagents could be used to carry out the following transformation? So it looks like we are starting with a ketone and reducing it to an alkane. So we've learned a couple of ways to do this. It looks like option A is the Clemmensen reduction, which we know that works. That does exactly what is shown. Option B, LiAlH with ether, that would get rid of the ketone, but it would not reduce it down to an alkane. So it's not going to be B. Option C, that is the thioacetal reduction that we talked about. So that's the one where we create this thing that's able to be reduced with Raney nickel. So that does work. So it's not all of these choices, but it is 2 of the choices. So option E is our correct answer. Now question 10, remember there was no question 9 because the formatting on this document was a little bit weird. So this one says question 9, but you marked it as, or it says question 10, but you marked it as question 9 on your Scantrons, hopefully. So question 10 says, select the structure of the major product in the following reaction. So we start with a ketone and react it with this peroxy acid. We know that it's a peroxy acid because it has these 3 oxygens in it. The molecule that we're reacting with it is symmetric right down the middle. So it doesn't actually matter if we attack on this position or this position because those are both chemically equivalent. And we know that the peroxy acid is going to add an oxygen in between the alpha carbon and the adjacent carbon. So it'll either stick an oxygen here or stick an oxygen here and then move all of the carbons down one. Which means that it looks like option 4 is the only one that adds the oxygen in the intended position. So option 4 is D, so D is the correct answer. Question 11, what is the predicted product of the reaction shown? So here we have a ketone that is reacting with a primary amine, and we know it's primary because it has only one bond to something that is not hydrogen. So I believe the shortcut that you were taught in class was if there were 2 protons, it's going to form a double bond. If there's 1 proton, it's going to just form a single bond. So we know that it's likely going to be option 5 because that's the only one that shows the nitrogen with a double bond, but I'm going to work through the mechanism just to show you, just to prove to you that that's the product that we're going to get. So this looks like it's going to be acid catalyzed because we have this H2SO4 in solution. So if it's acid catalyzed, we know that the first step is the oxygen is going to become protonated. So I'm going to show the lone pairs, The lone pairs on this oxygen are able to grab one of those hydrogens, becoming the ketonium product. And as I showed earlier, this has a resonance structure where the carbonyl carbon becomes positively charged. So when you do that, the nitrogen is able to use its lone pairs to attack at the carbonyl carbon and push one of these double bonds up onto the oxygen. And that product is going to look like this. The nitrogen is now positively charged because it has 4 bonds. We're going to have to protonate the OH group and deprotonate the NH2 group. So I can just show that as an intermolecular reaction where this oxygen has a lone pair that's able to just deprotonate, take one of those from the nitrogen, leaving us with this OH2 group is now a good leaving group. So this nitrogen, which now does not have a positive charge, only has 1 hydrogen and a lone pair. This lone pair is able to come back down to form a double bond and kick off this OH2 as a leaving group. So we lost water, we lost H2O, and we are left with this double bond nitrogen with an ethyl group and a hydrogen, which again is now positively charged because the nitrogen has 4 bonds. So we're going to do an acid workup, probably just using H2O, or you could use HSO4-. But either way, a base is going to come in and deprotonate this final hydrogen, leaving us with the product that looks like option 5. So 5 corresponds with E, so E is the correct answer. Question 12, which is the best sequence of reactions for the following transformation? So here we have a ketone that becomes an alcohol, but we've also added a methyl group, which means that it's probably going to be some sort of Grignard reaction happening there because that's one of the ways that we've learned to add carbon, to make carbon-carbon bonds. But then we've also added a nitro group here in the meta position. So in order to add the nitro group meta, we need something that is a meta director, which is what this starts out as. So this starts as a meta director, which means that we likely have to add the nitro group first, and then once the nitro group is added, then we can reduce the ketone into an alcohol, because this group is not a meta director. So the order of events are, we first need to add this nitro group so that it will add meta. Once the nitro group is added, then we reduce the ketone into the alcohol. So to add the nitro group, we're going to need to do HNO3 and H2SO4, which looks like options A, C, and D all start with adding a nitro group. So we know that B is probably not going to be the correct answer because that starts by doing the Grignard reaction. So probably not going to be B. And then option A, step 2 is to make a Grignard and then do an acid workup, which seems probable, but let's just check the other two. Option C and D both use reducing agents, NABH4 and LAALH, but neither of those add carbons. So this methyl group here that was added, that's not going to happen using NABH4 or LAALH. So we can't have C or D as well. Let's just verify that A is the correct answer, because it could be possible that none of these are satisfactory. So let's just double check A. So we have this methyl MGBR, which matches the methyl group that we're adding. And then we use diethyl ether as a solvent, ETO or ET2O, and then an acid workup with NH4Cl. So that's perfect. So A is going to be the correct answer. Sorry. Okay, question 13. What is the predicted product of the reaction shown? So we start with propanal, which is an aldehyde. We're going to add the dithiol and then acid workup and then Raney nickel. So we know that it's going to add something kind of similar to this-ish, but with the Raney nickel, that just gets completely removed and we are left with an alkane. So let's draw that out. So propanal is an aldehyde with 3 carbons. Hold on, I'm going to redraw this. So propanal is an aldehyde with 3 carbons. So 1, 2, 3, 1, 2, 3, and then aldehyde. If we add when we add dithiol in the presence of acid, we're going to convert the aldehyde into the following product. So both of the sulfur groups are going to be attached, and then there's 3 carbons connecting them. So like that. And then if we have Raney nickel, it's just going to completely erase this whole complex, and we're going to be left with propane. And then we're going to be left with propane. So looks like option 5 is our correct answer, which is E. Question 14, choose the reagents that would bring about the following reaction. So it looks like we are reducing from a carboxylic acid into an aldehyde. So we can't use our typical reducing agents like NABH4 and LAALH because those are too reactive and they will push the reaction past the aldehyde to an alcohol. So we have to use something like dibol H, which will only react once because there's only one hydrogen available to react. So option A, dibol H, is the only one that's going to be able to reduce. And finally, question 15, what impact does the following substituent have towards electrophilic aromatic substitution? So we have a methyl group attached to the benzene ring. Methyl groups are not able to resonate, but they are able to use induction to weakly activate the ring, and it's going to be orthopara-directing. So activating and orthopara-directing, that looks like option A. So A is the correct answer. All right, let's jump over to the free response. Question 1 says, circle which of the given aldehydes would react more quickly with LAH. Explain how you know. So LAH essentially acts as, LAH basically just acts as an H-, and it's going to attack at the carbonyl position, so either here or here, and it will reduce your ketone or aldehyde into an alcohol with an acid workup. So with an acid workup, this one would be methanol, and over here with an acid workup, we would get ethanol. So, factors to consider when thinking about this reaction. Steric effects and electronic effects are usually the things that I like to think about. So sterically, compound A has this slightly bulkier CH3 group. So sterically speaking, compound A has this more bulky CH3 group that's going to take up more space compared to these two itty-bitty hydrogens. So even though they're both aldehydes, this one is going to be slightly more sterically hindered, so this will react slower compared to compound B. So in terms of sterics, this one is going to react faster. And then in terms of electronics, if I can spell, we know that both of these structures are capable of resonating, so there's going to be a resonance structure in which there is a negative charge on the oxygen and a positive charge on the carbon. And again, because of the CH3 group here, this is capable of inductively stabilizing the carbocation, whereas compound B doesn't have anything to stabilize the carbocation, so this one's going to be less stable, hence more reactive. So both sterics and electronics are going to favor compound B reacting more quickly. Question 2, using proper curved arrows, draw the mechanism for the following reaction and predict the product. So it looks like we're starting with a primary amine and a ketone, which is going to lead to an imine product. So let's draw that mechanism. Because we have H plus and H2O, we know this is going to be acid catalyzed. So the first step is that this ketone is going to be protonated. So the ketone is going to grab one of those protons and create the ketonium ion. And we know this is capable of resonating, so I'm going to draw the resonance structure as well, which has the double bond breaking and forming a carbocation at the carbonyl carbon. So after protonating, the amine is able to attack at the carbonyl carbon's position because it's, So after protonating, the amine is then able to attack. So we'll show that here. And when it attacks, we get the kind of acetal analog of this reactions mechanism, where you've got two different products coming off of this original carbonyl carbon position. The nitrogen still has two hydrogens and this R group, which I'm just going to draw as an R group for now because actually maybe I can fit it. There we go. Okay, and we know that this is positively charged because the nitrogen has 4 bonds. The next step is we need to make the alcohol into a good leaving group, so we're going to protonate the alcohol, and we can do that by just stealing one of the protons from nitrogen because that was going to be the next step anyway, so we can just combine those two steps. So we can show this proton is being attacked, and those lone pairs are going to fall back onto the nitrogen. And when we do that, this OH2 group is now a good leaving group because it's positively charged, and this nitrogen has now had one of its lone pairs freed up, so it can form a double bond with the original carbonyl carbon. So it's going to reform the double bond and kick off water as a leaving group. So we've got a double bond to nitrogen. It still has one of its hydrogens, and it still has this cyclohexane ring as a substituent. And now again it has 4 bonds, so it's positively charged. So the final step is to deprotonate, jumping ahead. So the final step is to deprotonate the nitrogen. So I'm just going to show water as the base. Water has these lone pairs that are capable of stealing that proton and forming the final product. All right, so that is question 2. Moving on to question 3, predict each product for the following reaction below. You do not need to show the mechanism. Okay, so step 1, we have a benzene ring reacting with an acyl chloride in the presence of AlCl3, so this is a Friedel-Crafts acylation. the product of that is going to be a ketone added to the benzene ring. And then in the presence of excess methanol, we're going to have the acetal reaction happen because this is acid catalyzed. So with excess methanol, we're going to have this product. Oh, don't forget the double bonds. And finally, question 4, indicate which reagents would be needed to achieve the following transformation. Be sure to add acid-base workup where needed. Okay, so there's a couple of ways that we could think about this. We know that we're going to have to add a carbon-carbon bond to the ring, so probably some sort of either Friedel-Crafts acylation or Friedel-Crafts alkylation. If we think about our final product with this alcohol group, it might make sense to do an acylation because once you've acylated, you can then reduce the carbonyl carbon into an alcohol. So what I mean by that is we could start with this benzene, react it with If we react it with this ketone, the product would look something like this. And then we could use a reducing agent to reduce that ketone into an alcohol. So that reducing agent could be LAH, NABH4. Technically Dibol H works too, because it's secondary. So yeah, any of those. NABH4, LAH, technically Dibol would work. But you'd have to do that as step 1, and then step 2 would be an acid workup, because step 1 would create the O- group, so it would look like this. So you'd have to use step 2 as an acid workup. And you need to show that to get full points. Alternatively, we could try doing an alkylation instead of an acylation. So, goodness, that was a really ugly ring. Oh my gosh. So if you were to do an alkylation, you would need something like an ethyl chloride, again in the presence of AlCl3. When you do this, you create a benzene ring with an ethyl group. From here, you would have to find a way to add an alcohol to this. And I think the only way that I know of that you guys have been taught is to use Br2 and light or heat to do a radical reaction, radical bromination, which would put the bromine on this position. And then once you have bromine here, you could use what we learned, the reactions we learned in OChem 1 to remove the bromine and then replace it with alcohol. So you could do some sort of E2 reaction. E2 reaction would give you, oh my gosh, my rings look terrible today. Would give you a double bond here. And then from the double bond, you could do some sort of from here you could use acid catalyzed, what do they call it? acid-catalyzed hydration, so you're adding water across a double bond. You could use oxymerc-demerc. You can't use BH3-THF because that would put the OH group over here instead of over here. But any of those adding water across a double bond reactions should work. You also could have created a Grignard reagent, so you could add bromine and magnesium to your benzene ring, turn that into a Grignard, and then have that react with an aldehyde, or even like a CO2 like you guys probably did in your lab classes earlier this semester. So you could have done a Grignard reaction. I forgot to draw that one, but if you did that, that also counts. These aren't the only ways that you could solve this reaction. These are just 3 of like many different ways, but these are probably the most common ones that you guys are going to think of. If you thought of anything else and it works, I'm sure you'll get credit for it, but these are just a couple of examples. And that brings us to the end of this review. If you have any questions, please feel free to reach out and I will be happy to answer them.